Okay, so homework assignment was all the numbers between 1 and 1,000,000 that were evenly divisible by what, like 4 numbers? What were the numbers?
9, 13, 27, and 81.
Yep.
Actually, I was unable to upload it from a couple of days. Though my friends they have uploaded, mine is not being uploaded. Once installed, again it's being uninstalled.
So you couldn't get it uploaded to GitHub?
Yeah, the program was done already a couple of days ago, but it's not being uploaded though the link is given.
Okay, well for now, just zip it up and submit the zip file.
Oh, zip file?
Zip file, yeah. Zip up the folder and just submit the zip file. Or actually do this. Just copy this code right there and paste it into the box so you can get your submission, yeah, the submission box. All right? So, but do that now because I'm about to do the solution here. Okay, so you're supposed to go through all the numbers between 1 and 1,000,000. Was that right? All right, so we start off with our count. Go from 1 to 1,000,000. So what's that? 10,000, 100,000, 1,000,000. That guy? All right. And then you're supposed to count the number of numbers that are evenly divisible by, what are the? 9, 13, 27, 81? Okay. So if I mod 9 is equal to 0, or I mod 13 is equal to 0, or I mod 27 is equal to 0, or I mod 81 is equal to 0. If any of those things are true, we'll say count is equal to count plus 1. And then in the end, we should print out count. So that should be our number. Does that look right? Okay. So that's a reasonable solution to the problem. So we were able to practice our loops we looked at last time. Well, first of all, you got to practice making typos. So so we get to practice our loops, practice our variables, practice our Boolean expressions. Yeah, go ahead.
We have like int count and what we use I.
Well, I takes us
like I declare their like number.
Well, whatever. Yeah, I mean, there's the reason I call this I. The reason it's common for your counting variables. The common counting variables are I, J, K. That's just more common practice. These are really throwaway variables. When we think about a loop, right here we're looping on. We're doing something some number of times. Okay, we're going to be talking about the different types of loops today. But in this case, we're doing something some number of times, and that I variable is really a throwaway variable. It's not something that we're going to use again. It's just an index. But we're not even using it to index something. We will eventually be doing that. For right now, we're just using it to control this loop. How many times we go through it. Right?
I don't know if I would agree with that 179, 487. I did it different. I didn't do what you did up there.
I did exactly just
so I mod 9 is equal to 0, or it's equal or it's equal to 13, or it's 27, or it's 81. I mean, I think that's what the.
Well, no, maybe the way I did it completely. Maybe I did it wrong.
Yeah. Well, I mean, the question did say or, right? It was evenly divisible by any of those guys.
One number, like divisible by 9, we have done it separate for 9.
I almost did it exactly same.
So, I mean, the question asked, count the number of numbers, right? So we're counting how many numbers meet this criteria. That is the criteria that I is evenly divisible by 9, or I is evenly divisible by 13, or I is evenly divisible by 27, or I is evenly divisible by 81. It could be evenly divisible by multiples of those, but if it's evenly divisible by any of those, at least one, we'll increment count by 1.
I just counted each one.
So what do you mean you counted each one out?
I counted how how many were divisible by 9, how many were indivisible by 13, 27, 81.
Okay, so what yours didn't take into consideration was that some numbers might be evenly divisible by multiples of those.
And I broke that apart too.
Okay.
So that I treated the program that
Mm-hmm.
how many times did it find divisible by 9, count it. How many times did it find 13, count it. I just treated each one separately.
Okay, so you wrote yours like this. You said if this is true.
Yep. Then I did if statements for each one and all that. Yeah. And then I had separate energy counters for each one.
Well, do you need to have separate energy counters?
That's how I just broke it apart.
Okay.
I got it to work.
Okay. Well, how was the question worded?
I could have read the question wrong too.
Okay.
Yeah.
This one?
Yeah. Evenly.
Write a Java program that counts the number of numbers between 1 and 1 million that are evenly divisible by 9, 13, 27, or 81. Your program should display the total count to the screen. Alright, so 9, 13, 27, or 81. So the way I wrote it initially I think is reasonable. I'm trying to think if the number of numbers are evenly divisible by 9, you're counting all those.
Yep.
You're also counting the number of numbers that are evenly divisible by 13.
Yep.
The number of numbers that are 27 or 81, and you're adding all those together to get a final number. So what yours is doing, your number is probably a little higher because you're counting some of these numbers that are evenly divisible by 2 of these or 3 of these, and that's fine. I mean that as long as you have logic that's kind of in line with this, I can see you reading it that way. Yeah, my intent was to kind of build that OR looking thing, that guy. Kind of drill our Boolean expression thing we talked about last time. That's fine. All right, so any questions on this? All right, so let's look at where we left off last time. So last time we talked about this idea of a Boolean expression. So any expression that boils down to a single value of true or false, we looked at the arithmetic Boolean operators, so our normal mathy ones, less than this number, greater than this number, less than or equal to, that kind of stuff. We looked at our logical Boolean operators, so the and, the or, and the not. And then we talked about conditionals. So this is where we were using that Boolean expression, that any expression that boils down to a single value of true or false, in the context of this new structure, this if structure. And we use that right here. So if, so this whole big thing right here, at a glance, you might think that that's fairly complex, but ultimately that boils down to a single value of true or false, right? That's a Boolean expression. That's an example of a Boolean expression. Okay, and then what? I just introduced the loop kind of at the end and say this is just a loop. I didn't really go into loops very much. Is that a reasonable statement? Because we wrote this, but it's not in the slides. So let's talk about, we have 3 different kinds of loops that we have available to us. And remember, we're kind of building on this original idea way back on one of our early slides that the way human beings solve problems is we use our memory, we ask questions, and we do repetition. So here's an example of memory. Here's an example of asking a question. Here's an example of repetition. Okay, so we're seeing those things in every single programming language that we have. We'll have a facility for these things. There's multiple facilities for some of these things. All right, so let's talk about the loops. All right, so for right now, we're going to assume there's 3 kinds of loops in most of our modern languages. Some languages, specifically some of our newer ones, have added some additional convenience loops to them. We'll look at them at some point in time, but for right now, we're going to talk about structurally 3 loops. So we have a for loop, a while loop and a do while loop. All right, a for loop is a pre-check loop. We'll talk about what that means. A while loop is a pre-check loop, and a do while loop is a post-check loop. Now, each loop lends themselves to a certain kind of problem. That doesn't mean you can't solve different problems with that loop, but every loop does lend themselves to a specific type of problem. For loops lend themselves to counting type problems, where we know how many times we need to repeat something. While loops lend themselves to problems when we do not know how many times we need to repeat. I'll give you an example of that in a few minutes. Do while loops lend themselves to problems where we must do something at least one time. Okay, so at the top level, this idea of a while loop and a for loop, these guys are fairly similar in terms of problem solving. They're both pre-check loops, which lets it, because they're both pre-check loops, that lends them to be similar to each other. So they're going to be the ones we're most comfortable with. Now, what does it mean for a loop to be pre-checked? This has everything to do with the idea of the Boolean expression. It's when do we ask the question? So pre-check loops ask the question before we execute the body of the loop even once. All right, so pre-check we check the Boolean expression before we ever execute the body of the loop. So functionally, this means that pre-check loops will execute the body 0 or more times. There is no guarantee that you will ever get into the body of a pre-check loop. Make sense? Alternatively, post-check loops execute the body of the loop at least once and then check the Boolean expression after that first execution. Post-check loops will execute the body at least one time. So we'll say one or more times. All right, so there's a distinct difference between those. For loops and while loops are both pre-check. Do while loops are post-check. All right, so for loops lend themselves to the type problem where, to counting problems, where we're going to count from 1 to 10. Homework assignment, 1 to 1,000,000. That's why I introduced the for loop. It's good for counting type problems, problems where we know how many times we're going to go through. We want to do something 30 times, for loop's a perfect fit for that. Now, does that mean we can't do that with a while loop? Well, let's look at this. Let me show you the generic syntax for, well, here, let's just convert this to a while loop. So first of all, let me just talk about the different pieces here just so we see these. So in a for loop, this is our counting variable, typically how we'd reference it. You can actually have more than one variable there, but for right now, let's pretend that you can only have one. So this is our starting variable. This happens exactly one time.
So we can declare the integer I inside the loop.
This is inside the loop. And I'll show that to you here. There's going to be some differences I show you between for loops and while loops, so we're going to really talk about that in pretty good depth. So this guy happens exactly one time and gives us that starting variable. Here's our Boolean expression. This is a pre-check loop, so we will ask that question before we ever execute the body of the loop. Okay? So, for example, if I set this guy to be a number bigger than 1,000,000, and I run this, I get a 0. Count was 0. We never did anything in here, and then we went right to here. Because we never got into the body of that loop. Because we checked the Boolean expression first. And then this is what we do after the fact. So the order of operations is this happens once and only once. Then we ask this question. If it's true, we execute the body of the loop. Then we do this, then we do this, then we do this over and over and over again until this is finally false. When this is false, we fall past the end of the loop and continue on with the program. All right, that's the structure of a for loop. So now we're going to write this exact same program in terms of a while loop. All right, so I said before, while loops lend themselves to problems where we do not know how many times we're going to go through, although right here I'm applying it to a counting problem, right? So I'll start I off at 1. That happens before the while loop starts. That's a distinct difference between for loops and while loops. For loops bring this variable declaration into what's called the scope of the loop itself, and I'll show you what that means here in a few minutes. Okay? As opposed to a while loop where this variable is, the loop happens to use that variable I, but that I is not linked to the while loop. Where the I, when we were dealing with a for loop, is part of the for loop. All right? So this happens once. It's a pre-check loop, so we ask the question. If that's true, we execute the body. Very last thing in the body, I change the value of I, just like the very last thing that happened in the for loop was I updated I. It was back up top, but it was the last thing that I did. All right, so this should give me the exact same output. All right, so there's my while loop equivalent to the problem with the for loop. Okay, so now before we look at the do while loop, let's explore these two things. So I'm printing out count. What should the last value of I be? So every single time through here, I starts off at 1, then it's 2, then it's 3. When will this finally be false? When I is equal to 1,000,000, right? If I is 1,000,000, is 1,000,000 less than or equal to 1,000,000? It is. That's true. So I'll come in here and do the body again. Then 1,000,000 becomes 1,000,001. Loop back up. Is 1,000,001 less than or equal to 1,000,000? No. That's when it fails. So the value of I right here after the while loop should be 1,000,001. Okay, because we did increment it. So on 1,000,000, we went in here, did all the stuff. We incremented this value, looped back up, then we failed. So I is 1,000,001, and that's what will print out. So there's 1,000,001 for I. Make sense? All right, so let's switch this back to our for loop. So we're going to do it up there, so we don't need to do it there. What will I print out here?
I will be same.
Our theory would be it would be the same, right? Okay, pay no attention to the little squiggly red mark underneath the I. Oh, you think it'll be 1,000,000? See, I'm of the belief that when I hit this play button, Eclipse is not going to be very happy. All right, so it's going to tell me your program has some errors. When we hover over I down here, it says, I cannot be resolved to a variable. I've never heard of it. So we need to talk about a concept. variable scope. Scope is, so this refers to the areas of the program where a particular variable can be accessed. Okay? So for instance, let's say that I have a radio. Okay, my radio is in my car. We were talking about my car at the beginning of class, right? So radio's in my car. Can I turn my radio on right now? No. The scope of that radio is local to my car. I have to be in that area, inside my car in order to access that radio, right? When I'm in here, I'm in a different place. That radio is out of scope. Can't reach it. All right? Laptop's in scope. I'm messing with the laptop right now. All right, so variable scope says where are we allowed to access a variable and what dictates where we're allowed to access a variable. So we're going to say this is dictated by where a variable is defined. All right, so remember, variable definition requires type var name equals value. And really the equals value part is optional, but let's just leave it at this for right now. This is an example of variable definition. Okay, that is the variable initially being defined, as opposed to var name equals 7, something like that, or var name equals value. That is not a variable being defined. That is a variable being used and modified. In this case, we're changing the value of var name to be equal to value. But this line right here makes the assumption that var name has already previously been defined. So we define variables by putting their type first, then the var name, then the value. So as an example, we'll put the example underneath here. Int I is equal to 5. That's defining a variable named I. Okay. Int car is equal to flex. That's defining a variable. Well, actually, that's not going to work at all. We haven't introduced strings yet, but trust me, they exist. So here's a variable named car of type string, and it's equal to flex. This is me defining the value of that variable. Okay, I've defined the variable and given it a value in that line. As opposed to this, where I would say car is equal to fit. Car is already defined prior to this line. I am modifying its existing value. I'm overwriting its existing value to be a new value. That makes sense? So it's the variable declaration, the variable definition, this line, that dictates where we are allowed to access that variable. All right, so let's go back in here. So notice, right there I'm defining a variable named count. I'm changing the value of count right here, but I'm defining it right here. That's the guy that dictates where I am allowed to access count. Count is a variable defined inside of this thing called main, inside of this method. We're going to talk about those today, but from our work, in our perspective, our entire programming world lives right here. That's our world right now. So as far as we're concerned, this guy is a global variable that's accessible everywhere in our programming world. Our programming world is going to start growing as we start learning some stuff. But right now, our whole world lives between this opening curly brace and this closing curly brace. So this guy is available everywhere in there. Make sense? Okay, so its scope is global, is what we would say here. Later on, we're going to say it's a local variable of the main method. But right now, for us, it's a global variable. Now, int I, here's another variable definition. This guy is being defined as part of this for loop. So his scope is local to the for loop. This guy was born with the for loop, and he died after the for loop. He is now out of scope. When that for loop ended, so did all of that for loop's variables. Make sense? That's why we do not have access to I here. I scope was local to this loop here because it was defined as part of this loop, as opposed to this. So I could say int I and then I could say I equal to 1 there. And now it's happy to give me the value of I. Because technically I was defined outside of the for loop. He was given a value in the for loop, but he was defined outside of it. Make sense? So just that little change changed the scope of that variable. Now typically, the reason I mentioned that this whole IJK thing tends to be our typical counting variables, and that actually goes hand in hand with the number of loops you might put inside loops. So typically, the most number of loops you'd have inside of a loop is 3. 3 nested loops. You'd have a loop inside of a loop inside of a loop. Human beings can kind of hold things together for 3 dimensions. Once we get past that, things start going south quick. It doesn't mean we can't put 20 loops inside of each other. We just can't conceive that logic very easily. Okay, so realistically speaking, I is always the counter on the outer loop. J would be the counter on the inner loop. K would be the counter on the inner loop. Right? Not in our world yet. Our world right now is 1 loop. Right? We'll be adding a second loop inside of a loop shortly. We won't deal with 3 loops any time, in this class at least. All right? So these just happen to be naming conventions. Nothing keeps us from saying int elephant is equal to 1. Keep going as long as elephant is less than or equal to 1,000,000. And then say elephant is equal to elephant plus 1. I just proved why we don't use elephant as our counting variable. I is pretty easy to type. All right? So nothing keeps us from doing that, and I'm going to copy this. Java is perfectly happy to use the variable I've provided him. And once again, when I get here, it's going to give me the same error. It didn't care whether I used I, elephant, or some other made-up variable, because as far as he's concerned, none of those variables exist out here except count. Count is the only variable in scope, according to these guys, as well as this guy named args, which we're not going to talk about quite yet. We will talk about him, but not right this second. That makes sense? Variable scope?
So like here we are defining the variable within the for loop. So we can define it in anywhere else too, like in other loops?
Well, okay. Good question. So let me rewrite some stuff now. So do we understand the difference? I've shown you the scope with the for loop and the while loop. That one of them, the variable dies with the loop. The other one, we know a while loop doesn't give us the opportunity to define a variable as part of the loop. So a while loop doesn't come with his own local scope. So with that in mind, we can think of for loops as kind of special loops. They come with, kind of like a backpack. They have their own little scope that comes with them that allows us to kind of compartmentalize just that loop. While loops are really, really, really common, and this is kind of, I think, maybe what you're getting at here. So I'm going to dump all this stuff. All right, so this is going to go 0 to 9, then 9 back down to 0. So if I run this, I'm going to get 0 to 9, then 9 back down to 0, 2 loops back to back. But notice I used the exact same counting variable in both of these. I'm defining a variable here. I'm defining a variable here. Both of those variables died with their respective loops. Therefore, I can reuse that integer I variable all over the place when I use for loops. I don't have to worry, did I already define a variable, name that up someplace else, because they're all self-contained inside of this for loop. I is this little throwaway variable that I'm just using to iterate through some stuff. Okay? I is not a really important thing. It's not like remembering our name or our age or our social security number. It's just counting. Okay? Now, sometimes the variable you're counting on might be important. Okay? But as a general rule, when we're doing loops, counting type problems, this guy is just a necessary evil for going through the loops. All right? We may or may not actually use I. In this case, I am. I'm printing it. All right? But nothing kept me from just saying hello here 10 times. I didn't have to use I, so there's hello 10 times. All right? So I don't have to use this variable if I don't want to, but it is available to me if I'd like to use it. All right? But what's nice about these guys is I'm allowed to define I another time as part of a local variable for that for loop. But now watch what happens if I do this. Now I've defined I outside of the for loop. So now it's from our perspective, a global variable in our program, right? So our whole program lives inside of these opening and closing curly braces right here and right here. So this guy's available everywhere. So Java's pretty cool with this. It's like, fine, you didn't want to make this a local variable, the for loop, no problem. You don't have to make it a local variable, the for loop. But understand that that has some scope ramifications that we run into right here when I try to define an integer named I. And Java says, wait a minute. You already have an integer named I in this scope. This for loop scope lives within this scope. All right? So in my current scope, I already have a variable named I. I can't create another one. Now we're going to see when we get to object-oriented stuff, we're going to see that there's ways for us to create a more local copy of a variable, but in our world right now, that's an impossibility. Okay? So remember, I think I mentioned that you have to solve all of our problems in terms of what we've introduced, right? So we're evolving what we view as the programming world here. All right, things will be difficult enough as it is. All right, so unless you have a good reason to do something like this, one of the major perks of a for loop is that they have self-contained counters. I can just define a variable in there, and now I can use that same counting variable as many times as I want, knowing they won't impact each other because that variable was born right here and it died right there. It disappeared. Make sense? Okay, so that's this idea of scope. Super important. Not just understanding what scope is. So right now we're kind of in variable mode. We're going to talk about variable resolution. A variable is always resolved to its most local value. Now, for us, most local value doesn't really mean anything because we only have one local in our world. But later on, we'll have more than one local. All right, we're going to have a function inside of something bigger. But this is still a true sentence. So in our mind, local is just one place, and a variable is always resolved to its most local value. What does resolved means? Resolved means to replace the variable with its value. So with that in mind, we can think of variables as placeholders. When I say I, what I really mean is the value that I holds. And at runtime, I will resolve to its current value. Let me just get rid of this second loop here. I started off as 0. Then I'm asking the question, is I less than 10? This guy is a placeholder. I will resolve to its most local value. I's most local value is currently 0. So this question is saying, is 0 I will at runtime get replaced with its value. Is 0 less than 10? It is. So we're going to go and do this stuff. Then we're going to overwrite. This is the assignment operator. Single equal sign. It's a single equal sign. It's the assignment operator. This assigns the value of new value to var name, overwriting the old value in var name. That's the assignment operator. Not to be confused with the double equal sign, which is what? The equivalence operator, which is a Boolean operator. A double equal sign is going to give us a true or false. We don't want trues or falses when we're trying to give this dude a new value. Okay, so assignment operator is a single equal sign. Double equal sign with no spaces is the equivalence operator. Double equal sign with a space in the middle of it is an error. Eclipse will be perfectly happy to let you know that. All right. So, I, right here, is going to resolve to its most local definition, which is 0. Is 0 less than 10? Yes. Print out hello. Now we're going to set I equal to, so since it's on the left-hand side of the assignment operator, we're not going to resolve this side. Instead, this becomes the recipient of a new value. Okay, we're playing catch here. All right, so right here, I is the catcher, and he's going to catch whatever this value is. So on the right-hand side, we will resolve I to 0. 0 plus 1 is 1. We'll throw 1 into I, so now the new value of I is 1. It's overwritten to 0. Then we ask the question again. Is the current value of I less than 10? I resolves to its most local value, which is now 1. Is 1 less than 10? Yeah. Do the same magic. 1 becomes 2. Is 2 less than 10? Yes. 2 becomes 3, so on and so forth. Make sense? Okay. So variables always resolve to their most local definition. And that's important because one of the skills that we need to get is the ability to read code. Something that you're going to find that you're not very good at initially is, and I'm going to make the assumption that several of you, when you were working on this homework, got some very strange results, right? You typed in something funny, you forgot to do something, you had a semicolon somewhere, didn't know why you were getting. Common mistake is this. Somebody throws a semicolon at the end of that for loop. This stuff no longer happens as part of the for loop. Hello once. That's what this says. It says just print out hello. I put it inside these curly braces, whatever that means. But the for loop takes I on a voyage from 0 to 9 in this case. And this is the entire contents of the loop right there, what I have highlighted. That semicolon ended the statement. That's a common programming mistake. And then you wonder, well, why did it just print out once? And then you start screwing with numbers, right? Well, let's see, let's make it go to 100, and you run it again, and well, it's still just printing out once. Drives you crazy because you know where the problem was. Okay? So these are some things, this is a skill set you're going to build up, is learning. You're going to make those mistakes, and you're going to spend an hour staring at something that seems easy until you finally, you're like, was that it? With practice, you'll get better at this. So one thing to expect is, especially starting with the next assignment. The next assignment is substantially harder than this one. I was telling him before class, it's got like 5 parts. 4 of them are actually pretty easy. not much harder than this. But the fifth one is impossible, undoable, just not even completable. But what's bad about it is you're going to spend a week working on this. It's doable, but it is difficult. And then you're going to come in next week and you're going to watch me solve it in class. And you're going to be like, that was it? That's perfectly normal. All right, I've been doing this for a few minutes. All right, so you're trying, remember way back in our first class, I think I mentioned something like programming is like a sport. Okay, so for those of you who haven't programmed before, pick a sport you haven't done before. You're going to kind of be a spaz for a while, right? Okay, you're going to suck at it. You're going to be tripping over your own feet. Okay, that's normal. Make sense? Okay, so don't expect by the end of this class that you're going to be able to just sit down and type stuff out real quick and it all just work magically. What you can expect by the end of the class is you've been introduced to the stuff, and given enough time and enough frustration, you can probably get something reasonable done. Make sense? Okay, you're not going to be efficient. Okay, we're not playing professional basketball at the end if we're learning basketball. All right. So, in any case, this idea of variable resolution is really important because one of the skills we need to learn is being able to read code. Reading other people's code is going to help you when you try to copy your homework from Google. Okay. Now, the thing is, I don't even care if you do that as long as you learn. I'm going to find out on the exam if you haven't learned anything. But when you copy something off Google, make sure you understand what it's doing. So you need to be able to read that code. You need to be able to dissect it. You need to be able to walk through it and say, okay, well, what is this? This is a for loop. For loops repeat stuff. Okay, what am I repeating? Well, I'm starting a variable off at this, and I'm doing something in here. It looks like 100 times. Can I confirm it's 100 times? Yeah, it looks like I'm adding 1 to I each time, so it looks like 100 times. So if I'm going to translate what this line says, it says, do something 100 times. Okay, now what's that something? It's what's inside of these curly braces. In this case, it's hello. Print it out. This line says print out hello. I'm printing out hello 100 times. Make sense? So we need to be able to read that code. And they're not all going to be easy like this. Right? So, but there's two sides to this. One of it is one side is it's important for us to write readable code. Right? It's important that we indent. Eclipse does this for us, but it's so often I find beginning programming students that just have everything just left justified. It's just very difficult to read. Something like that. That immediately looks worse, doesn't it? Immediately looks worse. Let Eclipse help you. Huh?
This program is.
Oh, it'll work fine. Yeah, Java doesn't care. You can put your entire program on one line as far as Java is concerned. Okay? Not for human consumption, but yeah, Java doesn't care. This is human eyes only.
So it is automatically encrypted.
Say this again? Oh, it's automatically encrypted, yeah.
One line, no one can read it.
Now, something I like doing, very commonly you'll find in textbooks a syntax that looks like this. Something like that. That's a pretty common format where you'll see the opening curly brace on the same line, on the previous line, rather than below it. For those of you who've had programming before, my guess is you've probably seen it like this. Say this again?
They put all the 3 clauses in one line.
Oh, okay. So you want it to look like this. Like that? All right, yeah, even worse. But this is common. You'll see this. Is this easier or harder to read, do you think? Harder. Yeah, certainly. So why do you think this is so common?
Because experts write it, then they don't know what we are doing. They don't give much attention to it.
Probably save space in books. And,
Save space in books.
Paper.
That's it. This program's a lot shorter now. It's still arguably readable, but it's shorter. All right, so that's the argument. It's to save space in books. Frankly, I don't necessarily care, but if this is any indication, I'm not a highly organized person. but I always put my curly braces this way. So for somebody who's not naturally organized, to make it a priority to organize their code like this, maybe should speak something to the importance of organizing your code. Make sense? All right. And we're going to talk about some other things with curly braces here in a few minutes as well, but that's a decent starting point. All right, so we need to be able to read our code. We need to be able to read other people's code. And one skill that we need to do, we've talked about this already at a higher level, is we need to be able to slow down. Don't glance at something and think you know what it says. Actually walk through it and see what it actually says. Especially when you're debugging your own code. Because probably what you think it says is not what it says. That's why it's not doing what you think it should be doing. So slow down and read it one little step at a time and really try to understand what's happening. And that will be a skill you'll get better at. Far more important that you make mistakes now when our programs are still fairly simple and learn from them than it is to get something right because you copied it off Google or something and all of a sudden now you're not able to do this stuff because you haven't learned those troubleshooting skills. Troubleshooting skills are far, far more powerful than the do it right from the get-go skill. You know, that's we learn from our mistakes, not from our successes. You know, our successes probably deceive us. You know, ask any gambler, right?
Yeah.
Go to Vegas. I have a student who went to Vegas a couple weeks ago, and apparently he won like $5,000 or something like that. You know, so now in his head, he's probably a professional gambler, right? He can go to Vegas every weekend and win $5,000. So I'm waiting for him to want to set up a tent in my driveway. Okay. So we saw for loops and we saw while loops. Both of these guys are pre-check loops. The other guy is this do while loop. All right, so define a variable I. The scope of this variable is global inside of this entire method, right? It's defined outside of this loop. Frankly, even if it was defined inside this loop, it would still be global because do while loops are not like for loops. They don't get their own backpack. They don't get their own scope. But this guy's clearly defined before it anyways. Then we're going to do something. We're going to print out I. So I start off at 0. I will resolve to its most local value. Local value is 0. So this will print 0 to the screen. 0 becomes 1. Then we ask the question. Post check. We ask the question after we've run through the body once. While I is less than 10. Is the current value of I, which is 1, is that less than 10? It is. Spin back up. Print out 1. 1 becomes 2. 2 less than 10? Yes. Print out 2. 2 becomes 3. So on and so forth. Make sense? All right. So what should this print out? 0 to 9. There's our 0 to 9. All right. So let's go back here.
So every loop is doing the same work, so why do we have to do different ways?
Well, they're not exactly the same. You've already seen it not be the same once. Didn't you see us not be able to print out I with a while loop, and we were able to print out I with the for loop? Okay, I'm about to show you another one. Okay, what's the output of this guy going to be? Remember, for loops are pre-check loops. We ask the question first. 1 to 9? Zero to 9. Still going to be 0 to 9. Okay. I starts off at 0. We ask the question because this is a pre-check loop. So we ask the question before we execute the body. Is 0 less than 10? Yes. Print out 0. 0, oh, that was not introduced to you yet. It means the same thing. We'll talk about it today. In fact, we should probably talk about it soon because nobody writes it like this. All right, so 0 less than 10? Yes. Print out 0. 0 becomes 1. 1 less than 10? Yes. Print out 1. 1 becomes 2, so on and so forth. So this prints out 0 to 9. Okay? Actually, here, this will help us. There we go. We'll do the for loop first. That way, this variable lived and died with it. Now we're free to create an int I for our do while loop there. So this currently does 0 to 9. This currently does 0 to 9, correct? So we have 0 to 9 twice now. What's the output of this for loop?
0 to 999.
Okay, I hear 0 to 999. I hear an error. Okay. Now something I'm hearing a lot of here, or something I'm noticing, is a whole lot of guessing and not a whole lot of reading.
It's gonna be
1,000.
1,000. The first one's gonna be 1,000.
Okay. All right, so let's walk through it. I'm gonna go through it the way I would have expected you to go through it, that none of you did go through it. Okay, none of you did it this way. I starts off as 1,000. Is 1,000 less than 10? No. We're done. It's never true. It's a pre-check loop. 1,000 is not less than 10. Don't execute the body. Loop is over. First loop does nothing. Because this was false right off the bat. Going back here, remember we talked about pre-check loops will execute the body 0 or more times. We never executed the body here because I started off as 1,000, and right off the bat, 1,000 is not less than 10. So the output of this guy is nothing. So what's the output of the other guy? This guy. Output of that guy is 1,000 because it's a post-check loop. I is 1,000. Cool. Print it out. I haven't asked any questions at this point. Print it out. 1,000 becomes 1,001. Is 1,001 less than 10? Nope. Well, we're not going to do it again. So now we're done. So we're going to get nothing from the first one, and we're going to get 1,000 from the second one. So the output of this whole program should just be the 1,000 one time. Make sense? Okay, so that's different behaviors from two different loops. One is not better or worse than the other. We just need to understand how these loops behave because we want to use the right tool for the job. Okay, if you're doing some gardening and you have a bunch of gardening tools in the garage, each one of those tools has a purpose. You're going to grab the tool that's useful for the job you're about to do, right? Same thing's true with programming. I want us to start thinking about these things in terms of our toolbox. So now we know how to define variables, specifically just integers. Okay, pretty good with ints at this point. We haven't learned any of the other ones. We know how to do those. We know about if statements, right? We can ask questions, and we can even ask some complex questions using the ands and ors stuff, right? Great. Okay, as long as it deals with numbers. Right? We're kind of stuck with the number world right now. And then we have 3 different loops at our disposal: while loops, for loops, and do while loops. All right, so do while loops lend themselves to problems. I mentioned they lend themselves to problems where the body of the loop must execute at least once, where we must do something at least one time. Now, what's interesting about this is fact. Do while loops are easily the least common loops. Far, far, far less common than the other two. So if you were to look at a giant operating system, And actually, let me make a quick little comment while it's on the tip of my tongue here. Here's another truth. Call this a truth. All hard programs are made up of a bunch of easy parts. If you were to look at the source code for Microsoft Windows, you would see a lot of stuff, but stuff that looks kind of like this. It's not going to look like gibberish. It's going to look like programming logic. They're all solving weird math problems and stuff like that. And there's going to be a whole lot of it, so at any point in time, you might not be able to follow what the heck's going on, but it's going to look familiar to you, right? Okay. Let's see. So we know about the loops. Oh, I was mentioning. So do-while loops are the least common of our loops. But what's interesting is that a problem that they lend themselves to is among our most common problems that we solve. Can you think of a real-life problem where you must do something at least one time that you do likely multiple times every single day? Something in our computing life requires that something happens at least once every single time. It's going to have software related to it. Authentication. So if we're going to log into Amazon, I know sometimes our password's saved for us, right? But we have to pass it, our username and password, at least one time. If we screwed it up, then we got to pass it again, right? We got to read it in again. So do while loop, send my username and password, wait for the response. If I screwed it up, ask me for it again. Make sense? So authentication is one of our most common problems, and do while loops lend themselves specifically to authentication. But types of problems that do while loops lend themselves to are few and far between, but they do lend themselves to important problems. Okay. So let's look at iteration ops. We have the plus plus operator and the minus minus operator. Varname plus plus, plus plus varname. Varname minus minus, minus minus varname. This guy adds 1 to varname, adds 1 to the value of varname, and stores the result back in varname. So functionally, this is the same thing as saying varname is equal to varname plus 1. The plus plus operator functionally does that. I'll steal that definition. We'll throw it down here to this guy. This subtracts 1 from the value of varname and stores the result back in varname, so this is minus 1. Okay, now, there is a bit of a difference here, and it's important. It's important that we understand the difference, although I'm going to give you a good rule of thumb where you'll never get into trouble with this. So we're going to say int I is equal to 1, and we'll say int j is equal to 1. We'll do system.out.println. I'm actually just going to steal that because we're going to write several of these. I and j. So right now our program should output a 1 and a 1. Okay? Now I'm going to print out I++, and I'm going to print out plus j. And then I'm going to print out I and j. What do you think we'll print out here? Forget about the first 2 lines. Forget about the plus lines. 2 and 2. 2 and 2. Okay, we just advertised that the plus operator, this guy, adds 1 to whatever this value is, storing the result back in that value, right? So one way or another, I is going to become 1 bigger than it used to be. One way or another, j is going to become 1 bigger than it used to be. Both of these will be 2 and 2. Okay? Now, what will these guys print out? That's the bigger question. 1 and 2. Ah, he's been a programmer before. Okay. So, let me show it to you first. This will be 1, 2, 2, 2. Will be the output. 1, 2, 2, 2. When the plus comes after, then what happens is that this gets back to that variable resolution stuff. When the plus comes after, we resolve to the current value of I. And then we increment it afterwards. The current value of I before incrementing was 1. That's why it resolved to the 1. But we see right here, it did become 2. That makes sense? When the plus comes before the j, we immediately increment. We increment before we resolve the variable, getting the new value. That's why it's a 2. Make sense? All right. Minuses work the same way. My opinion, for what it's worth, don't play this game. If we do those like that, doesn't matter when they resolve, because we're not using the resolved value of them. We're changing I, we're making I 1 bigger than it used to be, we're making j 1 bigger than it used to be. Whether you said I++ or plus j, it doesn't matter, because we're not using the value right here. We know when this line is done, I is going to be 1 bigger than it used to be. We know when this line is done, j is going to be 1 bigger than it used to be. Pick your poison, which of those two you like using. Okay? Nobody's impressed if you save yourself 1 line of code by throwing stuff like that in there. Well, I currently want to get the real value of I right now, and then I'm going to increment. Why not just be clear to everybody and do your incrementing on its own line and then print something out? Make sense? You will never get into trouble if you explicitly modify your variables and not try to do these crazy combo lines. Having said that, understanding this material could help you do something convenient every now and then. Every now and then, being able to inline increment a variable might be handy, situationally. Okay, but let's say 99% of the time, you're not going to be backed into a corner where you won't be able to increment on one line and then use the variable on another. Most of the time, that's going to be perfectly acceptable, and you should take advantage of that. Okay? Nobody's counting how many lines of code you have. Make sense? All right. The longest correct program is far better than a very short incorrect one. All right, so now we're allowed to use plus and minus. So commonly you would see a for loop. You know, if we go to our go-to for loop, right now we're going to talk about our go-to for loop counting from 0 to 10, or 1 to 10, whatever, something like that. In a few minutes, when I introduce strings, our go-to for loop is going to be what's it going to take to spin through a string. That's going to be our go-to for loop. So these become kind of patterns of programming. Now that isn't to say you should memorize stuff, but there are certain patterns that we go back to very, very often. Make sense? You still got to let your mind get involved. We still have to problem solve this stuff. You're not going to just go on autopilot. And what's going to happen is over time, you're going to evolve how much you can passively do. Make sense? But you got to keep your standards realistic. I pretty often sit there and I'll write software while I'm watching Netflix. Most applications I can do that for. But if I'm really focusing on something and I'm solving a hard problem, I can't watch Netflix while I'm doing it. Okay? I can do Netflix while I'm doing this stuff, but that stuff I can't. So as you mature in your programming competence, you'll kind of realize where your limits are and when listening to music is okay and when you shouldn't. When you need to lock yourself in a room until you figure it out because you have to focus. All right, so we want to have these go-to patterns, so that's like the tool we grab. When you're doing gardening, if you're a competent gardener, you have a whole bunch of tools in your garage, and there might be something that you do gardening-wise very often, and you know it's this combination of these 3 tools. You don't even have to think about it. You walk out to the garage, you grab those 3 tools, you go out to the garden. Okay, and you get the job done. Okay? It becomes second nature. And the same thing is going to be true with some aspects of programming. So, kind of go-to loop for 0 to 10, 0 to 9, let's say. I is less than 10, I plus plus. That right there. This is a programming pattern. This is the loop that goes through 10 times. If you want it to go through 100 times, here's a loop that goes through 100 times. 1,000 times, there it goes through 1,000 times. Okay, that pattern is going to help you because now right off the bat you can say, oh, I want to do something some number of times. That's my for loop pattern. Make sense? And notice I did the I plus plus here. I could have easily just done plus plus I. Nobody cares because I'm not using the value right here. I'm just changing I. So as long as I is 1 bigger than it used to be, I'm perfectly happy. Now one thing you can't do here though is you can't say I plus 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 plus. Definitely can't do that many. That doesn't work. The plus plus operator operates on a variable thing. Variables resolve. So if I is currently 0, I plus plus boils down to 1. So effectively what I'm trying to say there is 1 plus plus. Well, 1's not a variable. 1's a literal. Now, have any of you ever tried to argue with numbers and say, 1, you're no longer 1, you're now 2? And we don't really have the power over changing numbers, right? So things that are literals, these are things. Okay, that's what they are. And we're not changing that. We don't get to change what a 1 is or what a 3 is. It just is. Okay, so when you resolve that variable, it's clear why that does not make sense. But if you just say I plus 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 plus, you might think, oh, well, why can't I do that? At a glance. Make sense? So we have to boil that down. We have to understand what's actually happening here. We'll resolve the I. So what does that actually resolve to? What I have highlighted there, based on what we just learned. Solves to 0. The plus plus came after. So that resolved to the current value of I. And then it changed I, but it still resolved to the current value of I because the plus plus came after. So this is actually saying 0 plus plus. Make sense? All right, so we do have, let me show you one other thing. So let's say that I actually want to say plus 2. So if we want to ultimately accomplish that, I is equal to I plus 2. So we can jump by 2's. We have these things called compound operators. Plus equals, minus equals, times equals, divide equals, and technically there's a modulus equals, but I'm going to leave that off right now. I plus equals 3 is the same as I is equal to I plus 3. So it keeps us from having to write I twice when we use the plus equals operator. So I plus equals ultimately turns into I equals I plus. That's how we can translate that. Same thing's true with the minus equals, times equals, divide equals. Now, if you don't want to, you never, ever, 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 ever have to use these. They are just shortcuts. I usually refer to stuff like this as syntactic sugar. Okay, this is syntactic sugar. Syntactic sugar. So here we would say I plus equals 2. And now it's I equals I plus 2. If you get comfortable with it, great. If you don't, you want to stick to the other ones, nobody's getting shot. Right? Like I said, a longer working program is far better than a shorter not working one. Okay? All right, so let's want to see here if did I introduce the primitive types yet? Have we talked about primitive types or Y2k problem? News to you? Okay, good. All right, so let's talk about primitive type variables. So in our modern languages like Java, we have two different variable types. We have primitive types and we have object types. We'll talk about our object types soon. Right now we're dealing with primitive types. So these are variable types that are built into the language and can only hold a value. That is the extent of their ability. This kind of variable can only hold a value, which from our perspective, that's the only kind of variables we've seen. So that's not all that impressive to us. So that's a variable. Well, when we get to object types, we'll see that object types can hold values, but they can also do more. They can operate, do functions on those values. Okay, so primitive type variables built into the language can only hold a value. That's the extent of their capabilities. So let's look at Java's primitive types. So I'm going to just get rid of this guy and stretch this out. So we have byte, short, int, long, char, float, double, Boolean. Okay, these are Java's primitive types. And let's see, let's look at C#'s Boolean primitive types. Done. So C# just has something called bool instead of Boolean. Want to see C++'s? That's C++'s. And C actually didn't even have a Boolean. It just did it with ints. All right, so this is Java. So let's talk about each of these. Whole number. Whole number. Whole number. Whole number. Whole number. Let's stop at those for right now. In fact, actually, let's not even bring chars into the context yet.
Char is character, not number. Is it like string in C++?
No, short's not a string. C++. Short's an integer type. All right, so byte, short, int, long. These are all whole numbers. All whole numbers. So the first question we might ask ourselves is, why do we need so many different ways of holding whole numbers? So for instance, a byte can hold the number 5. A short can hold the number 5. An int can hold the number 5. A long can hold the number 5. Why do I need so many different ways to hold the number 5? Well, so let's go back here. A byte is an 8-bit signed number. A short is a 16-bit signed number. An int is a 32-bit signed number. A long is a 64-bit signed number. Okay, well, so that looks more techy. What does that even mean? What does it mean for a number to be 8 bits or 16 bits or 32 bits or 64 bits?
0 and 1.
Okay, so a bit is 0 and 1, right? Okay. Have we talked about bits and bytes and those guys? Okay. We did or didn't?
Class, no?
Not in class, but we know.
Okay, so we have now talked about in class? All right, so I'd like to talk about that too. Because it is a very common misunderstanding. A bit is a 0 or 1. A kilobit is how many bits? 1024 bits. A megabit is 1024 kilobits. A gigabit is 1024 megabits, and you can say terabit, but well, we'll just put it on here for the sake of whatever. So 1024 gigabits. What's a byte? 8 bits. Kilobyte, 1024 bytes. Megabyte, 1024 kilobytes. Gigabyte, 1024 megabytes. Terabyte, it's 1024 gigabytes. All right, so the reason I like to discuss this is it's extremely common for people to misunderstand, even technology people, to misunderstand these kind of values. All right, so I'm going to see if I can trick you. All right. Do we all have internet at home? All right, what speed internet connection do you have?
56 kbps, kilobyte per second.
You have a dial-up modem?
It's like Wi-Fi from Warner, Time Warner.
Okay, so you have Time Warner cable, and how fast is your internet connection?
It's pretty fast.
Pretty fast, that's not good enough. You're an IT major, right?
Yeah.
Shouldn't you know exactly what the speed of your internet you're paying for is?
I never checked it. It's like some other guy.
But you would agree with me you should know, right? Okay. Anybody else want to take a stab? What internet speed do we have at home? 12 what?
Megabyte.
Okay. I got the little grin from him. I think he knows. All right. What else we have? 5.6 megabits. All right. Who's your provider? So Uverse. So you have Uverse internet? Okay, so yours is probably either 6 or 8 megabits per second. Could be 3. Are you paying like a cheap price, or are you paying one of the higher prices?
Cheap price.
Okay, yours is probably 3 or 6.
I checked with speed test. It showed like 5.
Okay, so actual speed, yeah. What I'm saying the speed is, we're talking the theoretical maximum speed. So when you did a speed test, you got something like 5 point some megabits per second. Okay, so you probably have a 6 megabit per second connection, would be my guess. Anybody else? Okay, so common misconception. Internet speeds are almost always advertised as megabits, this guy, per second. So for instance, I have pretty fast internet at my house. So I have 200 megabits per second. internet connection at my house. I'm a fiber tester for Time Warner. Now, a lot of people look at this, and actually we put a little slash here, right? And they throw you off here by you putting the big M in there. That makes you think it's faster. 200 megabits per second is actually 25 megabytes per second. So my maximum download speed is 25 megabytes per second. That's my maximum theoretical download speed. Now, in order for me to download at 25 megabytes per second, whoever I'm downloading from must be able to upload it to me at 25 megabytes per second. Maybe some of the big fish can do that. Okay, not very many. All right, so why do you need, am I just showing off? Is this is having 200 megabits per second just a waste? Who could ever use that? Because we're seeing this trend, right? We're seeing our internet connection speeds keep going up, 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 up. Why?
Maybe if you want to parallel downloading from several websites.
Okay, so let's take that. You're right. Let's extend that to what reality is today. Within a single home, you might have somebody watching Netflix. You might have two people watching Netflix. You might have somebody else playing streaming video games. You might have somebody else doing like a voice over IP phone call. So you have a whole lot of bandwidth hogging services that are happening within the house. So fine, one place isn't going to give me 25 megabytes per second download. But if I'm doing 10 things in the house through various people using stuff, and they're all using a little bit of my 200 megabits per second, nobody's performance is hurt, right? Because we're all using a fraction of the full bandwidth. Make sense? So that's why we want to have faster and faster internet connection speeds. And also our services keep increasing as well. So let's take Netflix as an example. Anybody in here a serial Netflix watcher? Yeah, I mean, why not? It's kind of shocking that our internet providers don't start screaming at us, right?
Well, they do.
Well, I've never had.
Well, I mean,
That's the net neutrality thing. Yeah. They're not screaming at us. They're screaming at each other saying, somebody's got to give us money for this, right? So when I was sick 3 weeks ago, I watched 7 seasons or 6 seasons of Walking Dead in 4 days. I mean, I could just lay on the couch and watch this for hours. And sometimes I'd pass in and out of sleep, and I have to go back and figure out, did I see this zombie or that zombie? But, the punchline is what keeps happening is the quality of the content we're downloading keeps getting bigger. A couple years ago, Netflix, the best you were going to get off Netflix was 720p. Then it was 1080i. Now it's 1080p. Now Netflix has specific shows in 4K. That's using a lot of bandwidth to send, let's just say 30 frames a second. At 4096 by 68 or something like that, is a 4K resolution. And each one of those is, let's say, 32-bit color. You're talking about a lot of data as you're coming across your network connection in a very short period of time. Netflix, they should actually make a documentary probably on Netflix's compression. Because that's where Netflix shines, is they have a really cool way of streaming video to you in a very small footprint. They compress the video quite a bit. Very interesting. But punchline here for us, and the reason I like to take a few minutes for this is we have a perception as technologists that we know these things because we've heard of them. That's different than knowing about them. All right? Because we see all sorts of different things around us get measured in different measurements here, right? Our hard drives are measured in terabytes. Before that, it was measured in gigabytes. Before that, it was measured in megabytes. Right? Way a long time ago, they were measured in kilobytes. Okay. Our internet speed is measured in megabits. And sometimes you'll walk into places like Best Buy, you'll see a hard drive, but it won't be a 3 terabyte hard drive. It'll be like some gigantic number of bit hard drive, just with like the zeros wrapping or something. And the average consumer is going to look at that and say, oh, gigantic number, this must be huge. I don't know if Best Buy quite does it to that extreme anymore, but they've done that before, where they try to misrepresent something accurately, but to the average consumer, a bigger number equals bigger, even though the measurement might be a different value. Okay, so kind of back to what we were talking about here. We have, no, first of all, a signed number is a number that's capable of holding positive and negative numbers. That's what a signed number is. So we have a byte, which is capable of holding an 8-bit signed number. We have a short, which is capable of holding a 16-bit signed number. An int, 32-bit signed number, along as a 64-bit signed number. Now, anytime we have a signed number, one of these bits is going to be used to hold the sign. So that means for a byte, only 7 of the bits is for the value of that number. One of them is for the positive or the negative. All right? So this is plus or minus, let's see, positive, negative 2 to the 7th power. That's what a byte gives us. This is positive or negative 2 to the 15th. Positive or negative 2 to the 31st. Positive or negative 2 to the 63rd. That's the range of values that fit in a byte, or short, or an int, or a long. This is negative 128 to positive 127. This is negative 32,768 to positive 32,767. This is negative 2.1 billion to positive, well, to 2.1 billion. I think this is something like negative 4 quintillion to positive quintillion. Big number. Okay? So, that's the range of values we can hold. Follow-up question. Why do we have so many different ways of holding numbers? Could I hold the number 5 in any of these? Okay. But why do these exist? How much memory do you have in your computer? 8 gig of RAM? Okay. Everybody in here know how much RAM they have in their computer?
Yeah, I have like 3, 4.
3 or 4? Oh, you're embarrassing yourself. If you're an IT major, you should know what your internet speed is. You should also know what how much RAM you have in your machine. You should know what your processor speed is. You need to know about computing. Okay, you don't have 3 gigabytes of RAM in your machine. 4 would be a fairly common, low, embarrassing type number, but common.
I don't need more than that.
What do you run in DOS still?
Is Windows 10 64?
I would venture to say you are hurting by only having 4 gigabytes of RAM on Windows 10. You must have really low standards when it comes to things opening. All right, so we have 4 gigabytes. I assume nobody has less than 4. Okay. How many people have at least 8? At least 16. No 16s in here? But still, 16 is not like out of the question today. I have one of my undergrad students, I think, has one of them is 32, and he was the high one for a long time. And then now one has 64. He built a gaming machine, just specifically wanted to max it to 64.
What does he do with that?
He probably plays, I don't know, Hello Kitty Island Universe or something. And I was like, I mean, he's not using 64 gigs of RAM, but he has it.
You know, I read that. I find that a waste. I mean, you get to a certain point, you know, me personally, if you need that much more memory and processing and all that stuff, then, you most computers now can run virtual hosts on them. Split it up, slice it, make your computer do more by slicing it.
Well, possibly, because then it has overhead. And the overhead, now you're sharing resources, and the slowdown for that is the hard drive. But regardless, for a developer, if you're a software developer, minimum RAM you should have is 8. Realistically, I would say with the modern OSs, 16. When so like right now, I'm on a Mac. So when I was running Yosemite, the previous Mac OS, 8 gigabytes was plenty. And when I upgraded to what's it called? El Capitan. I started noticing substantial sluggishness with some of the development stuff when I'm using Xcode or something like that. So I would say for a developer running a newer operating system, 16 gigabytes is probably reasonable. I don't think any more than 16 is necessary. Realistically, the number is probably 12. That's probably the real number is 12. But if you have 8, you're going to bump it. You probably bump it to 16. You don't bump it to 12. But in any case, this machine is from 2012. I think it was a mid-2012 laptop. And it has 16 in it. So, but I do a lot of programming competitions and stuff with it, so I maxed it when I don't think you can get more than 16 in a machine in 2012. Glad I didn't pay for it. I think this is a university submitted machine or something. But in any case, as technologists, we should know about this kind of stuff. Okay? I mean, even if you cry yourself asleep at night because you only have 4 gigabytes of RAM, that's okay. But you should at least know. All right. So, but really, that's an important thing because we see it in our IT program. I mean, you guys will take the networking class and stuff like that. If anybody should know about what kind of technologies they're surrounded by, it's you, right? You're the experts. You're supposed to be the experts. So take some pride in that and know what kind of technology you're working with. All right. So back to our question. Why? Is it charging now? I just noticed my battery life was at 30% and the little green light wasn't on here. Oh, we'll see what happens. Okay. So, well, there we go. Why do we have so many different ways of holding signed numbers?
Because of the memory and the program can run easily if it's smaller.
Okay. Well, so let's look at something here. So let's say we just always used a long 64-bit integer. Okay. So we'll go lowest common denominator, 4 gigabytes of RAM. All right. So 4 gigabytes of RAM, that's 4,096 megabytes times, well, we have to go to 64 bits is 8 bytes, right? That's what 64 bits is. It's 8 bytes divided by 8. Okay. So 4096, that's megabytes, times 1,024, that's kilobytes, times 1,024, that's bytes, divided by 8. 536,870,912 longs that we can store. So we can store 500 million longs in his pathetic memory. Can you imagine writing a computer program that's going to require 500 million variables?
That's more than enough for me.
Yeah, so we would say that memory is not a problem today, right? That a fair enough assessment? We don't care today. Java is based on C++, which is based on C. When did C come out?
Long time ago.
Long time ago. 1968-ish, somewhere in that ballpark. Did they have 4 gigabytes of RAM in 1968?
Yeah, they had a state to assign that memory to.
Yep.
4 gigabytes hard.
You just need the circuitry to support it, and we didn't have the technology small enough to do that.
1996, I had a computer that shipped with it was a 486 DX2 66 megahertz computer. Had to wait for the chip to get released. Just had 8 megabytes of RAM and a 420 megabyte hard drive. That was a bleeding edge computer in 1996. Just like $5,000. That was a ridiculously advanced computer in 1996 for a consumer.
Wait a minute, you had a 46? Pentiums were all Pentium 60.
Shortly after. Pentiums came out in 97 or 98. Yeah. I specifically had to wait for this chip to release. So, 6 months later, I decided, you know what? I'm going to double my RAM. I'm going to get another 8 megabyte chip and take my RAM to 16 megabytes. 1996, how much do you think an 8 megabyte memory chip cost? What?
It was probably close to about $800.
Yeah, a little higher, but about $1,000. $1,000 for an 8 megabyte chip.
Yeah, it was about $120 a meg.
Mm-hmm.
You can buy a laptop.
Right. $1,000 for an 8 megabyte chip.
I don't think you could have got an 8 megabyte chip in itself either. You had to get
2 4s.
Yep.
Yep. All right, so how much is memory today? If you don't want to go on the cheap and you just want to run out to Best Buy and pay retail, you could probably pick up, 8 gigabytes of RAM, 2 4s for maybe $70, something like that. If you want to go online, you can go a little cheaper. Probably get that same for $45 online. So when you actually do the math, roughly we pay less than a penny per megabyte today. A penny per megabyte. $125 per megabyte in 1996. Do you think it was maybe more expensive than that in 1968? Well, you weren't buying megabytes back then. You were paying like $1,000 for, a kilobyte, okay, back then. So in 1968, when this language was conceived, when it came out, and these primitive types were initially defined, memory was at a premium. Memory was really expensive. Easily, through the late 90s, memory was easily the most expensive part of your computer. I mean, it was prohibitively expensive. So we had to be good caretakers of our memory. Now we're on the other extreme. We don't care. Like I mentioned, I have students at 64 gigs just because I can. I found a good deal on Newegg or something like that. I think there is, I think Samsung, I don't think they've released them yet, but they're about to make 32 gigabyte sticks. Single RAM stick. And if you have 4 or 8 slots, you're going to get some really crazy numbers. So, but the punchline is that memory is now considered cheap, right? Who cares? Oh, you got bad system RAM? Well, even if it might be bad, throw $30 at it, put brand new RAM in there, we're good. Move on with life. It's like it was acting flaky, not anymore. Now it's brand new RAM. So in 1968, RAM was prohibitively expensive and prohibitively small. Forget about the cost, it was small. So we had to be careful about how we stored memory. So as a programmer back then, we always wanted to make sure that we used the smallest possible data type that we could use to store the value we needed to store. If we only needed to hold the numbers between 1 and 10, we should store that in a byte. fine, it's still overkill, but not as much of overkill as storing it in a long. That's a lot of wasted space. You know, a long might have been, you know, a tenth of your computer's RAM in 1968. Substantial, right? 10 total variables? your $500 million was going to work out okay with you, but we might need more than 10. All right, so how many of you have heard of Y2k Bug? All right, what is the Y2k Bug?
Short explanation.
Oh, it doesn't.
Y2k Bug was basically a programming mechanism prior to the year 2000 where developers would store year values in 2 digits, not 4 digits.
Mhm.
And what ended up happening was, as it was approaching the year 2000, a lot of computer systems did not roll over correctly, especially when using the 2-digit storage. And it was done for space saving.
Mhm.
So the fear was, or it was proved, you know, depending on your programs, some of them would reset back to the year 1900 or whatever, or your BIOS was unable to support it, or any number of things. So there was a lot of rework and fixing and patching.
Yeah, I mean, at the end of the day, the punchline is this. Because of this memory issue we just talked about, a whole lot of developers, maybe rightly so, chose to store years as 2 digits instead of 4 because it saves space. Great. Well, they operated under the assumption that, oh, these programs are going to be replaced before this is a problem. Some of these programs were around for 20 years. They weren't replaced, and they're running like power grids and stuff like that. And one of the issues was, and you had all sorts of issues as he pointed out, but when it came to, a lot of it was actually economic. It was billing issues. When it went from 99 to 00, is that 2000 or is that 1900? All of a sudden, electricity meters were going to be off. All these things were going to be off based on billing cycles. So all these programs had to be converted to up to a 4-digit year. And it wasn't a hard conversion. It was just tedious work. Because everywhere in the program where you did this stuff, you had to change it to 4 digits. And then it was also, they had the opportunity to make other updates since they were already in there. You're going to break stuff, you might as well fix other stuff, that type of thing. So Y2k Bug was kind of our evidence that programmers used to have to really care about this. Today, we don't. Realistically, as a developer today, we're going to use an int as our kind of go-to whole number. If that's not big enough, we use a long. If that's not big enough, we move over to the object category, and there's some objects that allow us to hold larger things. All right? You will never see a Java developer use short. You might see some old C or C++ programs use short because they came out during a time period where this was still a problem, or they're left over from that time period. So for instance, a lot of systems programming stuff which is written in C, even though that memory issue isn't an issue today, you might have a library that was written in 1974 for the Unix operating system. If it's not broken, why should they change it? Right? So you might still see some shorts in there, but for no other reason than that's how it was originally written. All right? Plenty of memory today. So you'll never see a short in Java. Bytes you will see, but not for the size. You'll see bytes for network type communication when you're streaming things in 1 byte at a time. So it's more of, that's the type of thing we're getting to digest the information, so we'll go ahead and get bytes in. All right, so these are our 4 types here for whole signed integers: byte, short, int, long. Now char. A char is a 16-bit unsigned number. This is 0 to 65,535. Now, when we hear char, that probably sounds like a character to us, right? So these are variables built for holding characters, is what we would assume. Let's look at this. So the char primitive type. So for instance, A is a char. B is a char. The char 7 is a char. Chars are always represented with single quotes around them. That's what dictates that it's a char. So if I want to define a variable for holding a char, I can say something like char C is equal to the character 7. Just like I defined an integer, name something, I could define a char, name something, and set it equal to a value, and that value should be a character value. Character values are notated with the single quotes around it. Make sense? Okay. So we're looking at chars here, and I see an A, I see a B, I see this character 7. Why is it that I'm advertising back here that chars are 16-bit unsigned numbers?
Because it's not a positive or a negative number. You're not storing for positive or negative.
Okay. So that explains the unsigned part of it. So I don't need negative numbers, so we might as well get all 16 bits, right? I don't need only 15 bits. I can use all 16 because I'm not storing a negative number. But why is it a number to begin with? Aren't they characters? Is A a number? Is B a number? Why are chars numbers? Clearly they're not. As a human being, when we think of chars, we think of things like this, right? Question marks and commas and letters and numbers in character format, right? That's what a char is. Computers like numbers. Human beings, we can tolerate numbers, nice whole numbers. We don't like the bits, right? We already talked about that. We like the bigger numbers, okay? But we mostly like pictures and words, right? The more expressive something is, the better for a person. Computers, they kind of just want to stick with those numbers. Okay, that's what they're good at. So what we have here for the character primitive type, if we were back in the C days, C and C++ days, character primitive types were actually stored as unsigned 8-bit integers, 8-bit whole numbers. There was 256 unique ones, 0 to 255, in fact. So in C, we had 0 to 255 were the values that chars could hold. And this mapped to something called the Ascii Character Set. American Standard Code for Information Interchange. This is a giant, well, not even that giant, 256 character lookup table where you had a number on the side, and each number corresponded to a character. So the computer would store the numeric representation, and then because it was a char, before something got displayed on the screen, it would get translated, it would get mapped on that table to its character equivalent. Make sense? Now, with our more modern languages, somebody who finally woke up one day and said, you know what? There are more languages in the world than just English. In fact, we didn't even use the entire 256 characters. We just used a subset of those for the English alphabet. And then we had a bunch of other characters that were we had pictures of playing cards, and then we had little smiley faces. Oh, we just wasted characters, threw things in there. Okay, but as we've discussed before, many of us speak another language in here, right? Okay. Well, many of us also speak English because you're almost forced to, right? I mean, that's the world we live in, isn't it? Fair, not fair, doesn't matter. That's the world we live in. Okay, so I don't know, maybe the American Standard Code guys were good enough. Screw the other languages. Take it or leave it. But in any case, there is some advantage of being able to digitally represent characters in other languages. I'm sure many of you like reading websites and stuff like that in your native language. I mean, you get more out of it because you're having to fumble over some of the English words, and half the English stuff isn't written very well, whatever it is. But so we live in a global economy now. So Unicode is this new character set. So we're going to say in Java on, we had 0 to 65,535, and this guy's called the Unicode character set. Now the first 256 characters of the Unicode character set are the same as ASCII. So Unicode is a superset of the ASCII character set. All right, so we kept ASCII and just added a whole bunch of crap on top of it for all sorts of different languages. I doubt very much it covers every single language in the world because there's some pretty interesting, weird African dialects and stuff like that. There's a lot of languages in the world. But it covers a lot more of them, all right, than ASCII did. So that's the idea of the Unicode character set. Now, what's interesting, though, is most of our terminals that you work with in your operating systems are only ASCII aware. You have to get some special software. I mean, it's not that they don't exist, but most of the stuff that's built into your operating system, the kind of the default things, are only in ASCII mode. So even though you have access to all these things, you just get a zillion question marks because it doesn't know how to translate from a number into, you know, some non-standard, let's say, Unicode character. All right, so that's the character primitive type, the char primitive type. And this thing keeps kicking off. That thing's on. Yeah, whatever. We'll be taking a break in a second anyway, so I can screw with it. Okay, so that's the Unicode character set. So just real quick before we take a break. What do you suspect that will output? It should be the alphabet. So we're going to start a variable C off at the character A, which has some numerical value behind the scenes, right? As long as the current value of C is less than or equal to Z, print out C, and C will be flagged as being a char type, therefore it won't print out the number, it'll convert it to, it'll look it up on the Unicode table and give us the character that's stored in there. Each time through we'll say C++, well, the plus just adds 1 to a number. Well, as we just learned, chars are actually numbers. So that's perfectly reasonable. So we print this out. We see that there's our letters of the alphabet.
So you capitalize that, or you count it in the capitalized?
Yep. Because those guys are next to each other in that. And what I can show you here, let's just do one more thing on the so we're going to call this typecasting. Now that we started talking about a couple of types, sometimes we want to convert one type into another. Now, not all types are convertible, right? So it has to make sense. So for instance, you can't convert an ice cream cone into a car. Doesn't. What do you expect? If you try to make an ice cream cone into a car, you're not going to get a very good car. Right? So similarly, if we try to take a char and convert it into an int, that should work because we know that under the hood, chars are actually represented as integers, right? So the syntax for typecasting is destination type, followed by per value. So for instance, if I have char C is equal to A, I can say int I is equal to the integer version of C. That will cast C into an int. And just to show you how this works, I'll come in here, and rather than printing out C, I'm going to print out the integer version of C. This should tell it, Don't treat C as a char. Treat C as a number. Show me the Unicode values that we're going through for A through Z. So that's 65 to 90, as opposed to lowercase a through Z is 97 to 122. That makes sense? And then to prove my last point, we're going to start int I equals 0. I is less than or equal to 65,535. I plus plus. Let's print out the char version of I. And what we're going to see here is a whole lot of question marks because this guy down here only knows how to do some of those. Oh, there we got some, like if Chinese or Japanese characters. You know, actually that's new. That's new in Eclipse that it's been able to do that. Oh, look, I got some good stuff there. I'm guessing we're flowing through some Cyrillic stuff in there. All right, more cool looking stuff. Man, those are awesome looking. You can use those. You could use some of those characters as your own. Like you're gonna make a text-based like Galaga game. It could be the spaceships. All right, so kind of makes sense. All right. So let's take about a 20-minute break. We'll come back and we're going to start talking about strings. And I'm going to